All right, guys, I know it's hot, it's Monday, but we do need to do at least a little catch up. We're gonna start this one. I'm not going through all this today, so it's okay. But it's important to get this one started. Last one I talked about pointers, which is a very, very practical application to how computers work. Today we're gonna take a step back and start thinking more theoretical about our computer programs, and namely how we're gonna do performance analysis. So I said first we're going to do theoretical, and then we're going to start that today. And then next class we'll go into a little more of theoretics, and then actually go back to empirically how do we deduce the performance of a program. But it's very important to understand the performance analysis, because when you're writing your code, you need to at least have an idea if the performance is going to work for your application. And furthermore, if all of a sudden your program's running too slow, you need to at least have tools to evaluate why is it running too slow. And today we're going to at least start talking about complexity analysis, which is really the first step you should use for doing analysis of performance. Also, what we learned today we're going to be using throughout the entire course when trying to compare different data structures against one another. All right. So, the common collection or a dilemma is you have two good or more methods to solve a problem, and you need to choose the best one. Well, you could implement each algorithm in C and test to see how long each runs. And when I say the best in this scenario, I'm talking about best in performance. By the way, when you go in the world, another attribute is how easily can you program it, because right now people are the expensive thing, not computers. But let's just say for this course, we only care about performance, just to make our argument simple. How do we know which one's best? Well, we can implement both in C and then figure out how long it takes to run them. There are problems here. Different implementations may cause an algorithm to run faster or slower. Just because you understand how your data structure works, someone may implement it in a terrible way, which runs slow. Someone else may implement a terrible data structure in a really fast way and then make it run better. But that doesn't really compare apples to apples, unfortunately. Some algorithms run faster on some computers. We're going to kind of ignore that for this class, but when you get to architecture, you'll figure out why that's the case. And they may perform differently on data. For example, sorting often depends on what's being sorted. Like what algorithm, if it's already sorted, will return it basically after one quick pass. Another one still has to sort everything before it's done. But the one that ends on a one quick pass actually takes forever if it's not sorted. So there are different problems with this approach. So another one, we could characterize performance in terms of operations and then try and compare the two. Sorting, well, it's a number of times you compare two different values. Did y'all do basic sorting in OOP or procedural? Like bubble sort, insertion sort, yes, no, maybe? All right. Good, so this isn't new. Also, a number of times you swap, and those are two things you look into when you're sorting, because that's what you do the most of. Searching is a number of times you have to compare against an array, and then recursion is basically how many times you have to make that recursive call. So what's a little better is want to comment on the general performance. We could do this empirically, but instead we're going to do this analytically, which means we're going to assess everything from an abstract manner. We're not going to actually code it. We're going to evaluate what the algorithm does and then figure out how long it takes to do each step. Sorting, how many comparisons are needed for an array of size n? Searching, how many comparisons do we need for an array of size n? That's the question we're asking, because if we can minimize the number of comparisons, then chances are we know which algorithm is faster or slower. Sometimes it can be difficult to do this. Okay. Let's jump back to that in a moment. We are estimating. It's very, very important to understand that when you do this type of analysis, which eventually is going to turn into big O analysis, we are estimating. We're not coming up with an exact value. What actually happens on the computer is going to be many more steps than what you realize, but that's okay. We're actually going to estimate what's going on. But you do this all the time. This shouldn't be hard. For example, how many hot dogs tall is the Empire State Building? a lot. Nice estimation, but unfortunately subjective. We want to quantify it. 5,000 something.
Depends on the length of the hot dog.
Depends on the length of the hot dog and
How tall the Empire State
yeah, and how tall the Empire State Building is. Okay. Yeah. So it's 1,250 feet tall. If we assume a hot dog is 6 inches, then we need 2,500 hot dogs. If we ran 2,500 hot dogs, would that be the height of the Empire State Building?
Yeah, I'm not sure how you do that.
Let me put it this way. What's the probability that it is exactly 2,500 hot dogs tall? Unlikely. But are we in the ballpark?
Pretty close.
We're going to be close. That's the point I'm trying to make. That when you do this type of analytical analysis, you're not going to be exact. That's okay. You're just trying to estimate, and you do this all the time. I don't know how you'd string up that many hot dogs.
It's a long metal bowl.
I think you have to go straight through each one.
Yeah.
I can't. Well, the other problem is you'd have to like hold it here, and you'd have to have something up here sticking out to hold it down, right? And then if the wind blew, well, so we're in computer science. We don't deal with the physical world. It does weird things. Okay. Whew. I think I'm about ready to I'm going to get through about this much, and that's going to be about it. Oh, yeah. Analysis, an objective way to evaluate the cost. So, right, we're not being subjective. The answer is not a lot. We're actually going to come up with a number. Not that a lot's a bad answer at first, just that we want something more precise. We want to have a meaningful way to compare, and then you have two analysis. You analyze the algorithm, and then you decide its complexity. Okay, that's nice. We're going to skip that. Rules. To do this, we're going to simplify our lives as much as we possibly can. We're going to assume an arbitrary time limit. You can make it whatever you want. A nanosecond, a millisecond, a whole second, 10 years, I don't care. Whatever. We're just going to assume that each of these takes one time unit. Assigning, an IO operation, aka you get something from the keyboard. Single Boolean operations, numeric comparisons, any arithmetic operations, a function return, array index, a pointer dereference. Do all those take the same amount of time? No, not even close. But that doesn't matter because we're estimating. And when I say not even close, I really just mean number 2 is forever, the rest of them are at least in the ballpark. And these are going to be very obvious when we start doing them. So let's do this one first. Count equals count plus 1. And we're going to call that the cost C1. And then we're going to have sum equals sum plus count, and the cost of that is C2. So the question is, how much does the first line, C1, cost? AKA, what does C1 equal? Well, what's being done on that first line? Correct. So how many of those operations that we just talked about are being performed on that first line? 2. So the cost of C1 is 2. How about the cost of C2? 2. So the total cost is 4. All right. Not trying to be tricky. Oh, whoops. All right. So if statement. So these are simple. That's great. If statements are going to get a little more complicated. C1 is going to be the cost of that Boolean expression up top, which is just 1 because we're just doing one comparison. All right, great. And now we need to know what the cost of C2 is and the cost of C3, but it depends on which one we use on the if statement. Well, the cost of C2, you're doing a negation, that's cost of 1, and then you're doing an assignment. So C2's cost is 2 because you have those 2 operations, negation and assignment. C3 only costs 1 because you're just doing one assignment. By the way, this does absolute value. So this is why I skipped worst case, best case, and average case because this is a great example of it. The worst case scenario is if you take the if statement and you do the more costly operation, which means your cost would be 3 in the worst case. Best case is when you go to the second else, because it's just 1 plus 1, and your cost is 2. On average, what happens? Well, when you say average, you just kind of have to sit down there and figure it out. In this case, an if statement, you're probably doing half and half. So it's going to be the average of the 2, or aka 2.5. You good? Oh, I didn't tell you. What's the cost of C1? What's the cost of C2? What's the cost of C3? 1, because it's just a comparison. What's the cost of C4? 2. What's the cost of C5? All right. Cost. So what's the total cost? Ooh. Not necessarily. That is true, excuse me, if n is 1. That is true. Let me help you out.
Best case 7, worst case.
Actually, the best case would be 2 because you don't take the while statement. Well, 3, I mean. Actually, the best case is 3 because if you don't take the, you still have to evaluate the while statement, but if you don't take it, then you're done. Right? Right. So, but the first point is, that's a good point. What is always being done? Well, you have to always do C1, C2, and you have to do C3. So it's going to be 3 plus something, right? What's that plus going to be based off of? N. And I set it up such that you can just use n as a variable because you, if n is 0, then you multiply it by 0 and you're done. But how many times do you go through this while loop? Well, every time you execute the while loop, how many? What's the cost of executing an iteration of the while loop? Oh, not just 2. What? It's going to be the cost of what? 4. Good guess, but it's 1 more than 4. It's 5. Why is it 5?
Does this have to run the while?
The Boolean expression. So every time you run the while loop, remember, you have to do this, you have to do that, and you have to check it. So each iteration of the while loop is the cost of C3, C4 plus C5, which is a total of 5. So it's the cost is 3 plus 5 times n. Or if you want to write it out, when I didn't actually put it, you would, without even looking at the cost, C1 plus C2 plus C3 plus n times the cost of the while loop. All right, how are we doing? Okay, hot? Yeah. Oh, online student, you're doing great right now. All right, I think we'll do this and then we'll call it a day. All right, what's the cost of C1? 2, 3, 4, 5, 6, 7, 8. Great. Now, how do we go about figuring out what the total cost of this is going to be?
Break it down.
Break it down, right. So which one do we evaluate first? The innermost function. Excellent. All right. So what's the cost of the innermost function? I hope everyone, I'm going to erase this unless someone needs it. Good. And sorry, online student, you don't get to see this. So the inner while. Well, how many times does it execute?
1 plus 2n.
Hold on.
Why not 2?
Well, j starts at 1 and n, so as long as j is less than or equal to n, how many times does it execute? Sorry. I think you maybe were answering the wrong question. What did you say?
I said 1 plus 4n.
Oh, okay. 1 plus 4n. Oh, okay, I see what you're saying. Remember, the cost of the while loop has to include the Boolean expression as well, because it has to evaluate each time. So it's 5n actually is how many times, what the cost of that one is. So when I asked how many times does it execute, I meant n times. And what's the cost of a while loop executing in the inner one? 5. So the inner one is 5n. How about the outer? Well, ignore that while right now. Let's see, 1, 2. I ignore the inner while.
Yeah.
4. So it's just 4, right? 1, 2, 3, 4, because we're ignoring that while.
But don't we have to include the while?
We're going to. We're going to. But I wanted to show you real quick. So I think y'all are thinking about it the other way, the opposite way of I do it, which is fine. So so I think the way y'all are thinking about it is, what's the cost of executing the while loop or running it one time? So it's 4 plus 5n, because it has to execute the inner while loop, right? And then how many times does this execute? N times. Okay? And then, what do we need to add to all that? 3. You're close, because remember, it has to evaluate that while loop the first time. The while loop's tricky because its evaluation technically happens at the end, even though it's showing to happen at the beginning. And when it starts, it does its first initial evaluation. So it's really 3 plus. If you wanted to math it all out, it'd look like that. Hey, notice you have an n times n here and just a single n right there. That'll be very important for next class when we get to big O analysis. Are there any questions about this? All right. I have pushed the pointers. Let's see, lab. Whew, burning hot in here. I think that's going to be it for today. Any questions? Nope. All right, guys. Well, welcome back. And I will see you on Wednesday.